Hello again, let's get more into the practical aspect of what we do at our OtterSec cryptography team. So first, who am I and how I got here? So I got into security while CTFing here with DragonSec and play also for teams organizers and Team Europe. Recently I finished my master's and ended up at OtterSec since December as a security researcher and auditor. So what I'm going to talk about is I will give you some introduction into the cryptographic primitives that are used in zkVMs and, well, what zkVMs even are. And then I will show you how it all goes wrong and, well, what are the takeaways of these design choices and pitfalls that we will see. So first, let me talk a bit about, well, the main culprits of all of this. First, to understand what a zkVM is, we need to know what, well, an interactive protocol is. And essentially, for our sakes, this is just one version of it. It's a protocol where a prover and a verifier exchange messages, and in the usual sense, the prover sends messages and the verifier just samples some random challenges that the prover has to compute some response based on those challenges. And here it's important that the prover's response after receiving some challenge cannot be computed before receiving that challenge, because otherwise the entire system breaks apart. But this is not efficient if we have a complicated protocol that's going to have a lot of rounds, a lot of messages. If you send this over an internet, prove something, it's going to take a lot of round trips. It's going to take a lot of time. And that's where, well, we try to make it instead non-interactive. And we do that with the Fiat-Shamir transform, which allows us to replace the verifier, at least when we're constructing the proof, with a transcript, which is essentially just some state that when we absorb some commitment, some message into the state, something gets hashed, and that state gets updated. And when a verifier would then send the random challenge to the prover, instead we just hash something in the state of the transcript to get essentially an equivalent random challenge. And we continue the proof that way. So like that, the prover can just do the entire protocol on its own and send all of the messages that it would like send one by one in an interactive proof at the same time inside a proof. And the verifier can then do essentially the inverse of that. That is just one after another append, well, absorb messages that the prover would normally send it over a wire into the transcript, and then squeeze challenges from the transcript. And then once it recovered the entire state, which is essentially the messages that both the prover and the verifier would send to each other, it can just take all of that data and just run a verify function on it to verify the entire proof, if it was correct or not. So here, yeah, we just have one round trip, so now we become happy. But as we'll see later, this can also go wrong in many, many ways. Now with this slide background of, well, zero knowledge, or at least proof system, what even is a zkVM? So it's an acronym for zero knowledge virtual machine. So first, why is the virtual machine relevant there? Essentially, what zkVMs do is prove some statements about programs running in the virtual machine. So usually, these are RISC-V or similar, maybe modified RISC-V virtual machines, for which we have some program, we have some public input, and some public output. And we claim that if we input, well, the input into that program, we will get the output claimed. And what the proof actually claims then is that there exists some trace, so some execution of instructions in that program, that when you give it the input, the output actually matches that was claimed. And where the zero knowledge part comes in is, in the end, ideally the verifier does not learn the transcript. So it does not know what the program did while it was computing stuff. It only knows what the input was, what the output was, nothing in between. which can come in handy, especially in some slightly more special cases where we might have some private inputs as well. So not everything is public. But the more important part here is that usually this lets the verifier check the program's execution without actually running the program and do it in a much more efficient manner. So here is a diagram of how it might look like. So yeah, we have some public statements that we use, and then the prover runs the program, records the execution trace, computes the proof, and then however the proof, like whatever the proof defines, it should look that the computation should look like happens. Then usually we make it non-interactive, add a Fiat Shamir transcript, and then that entire proof gets sent to the verifier, and the verifier checks everything. It's just a very complicated proof system. Nothing really more happening in it. So now let's take another look at one of the components that's very often used in zkVMs, and that is the suncheck protocol, which in the following slides you will not need to really follow every detail on the slides. They're just there for completeness sake, and if anyone is really interested in it. But the suncheck protocol essentially shows that a sum of evaluations of some polynomial ends up being some claim h. So that's about what you need. And I will use this h as the claim of sunchecks protocols for the rest of the presentation. So yeah, and well, how do we actually do that? Because if I go back, this sum might contain many terms. So like here, if we have n equal to, I don't know, 20, this, OK, 20 is maybe it's more like 30, 40, whatever. This might take very long to compute, and we don't want the verifier to take long to compute stuff. The prover, we're fine with being slow. The verifier needs to be fast. So yeah, now that's exactly what the suncheck protocol does. And how that works is, first, the prover computes this claim, h. So if the prover is honest, just computes the actual sum, sends it to the verifier. And then since, well, the verifier doesn't want to compute all of this again, the prover removes all of the variables except the first one and sends a polynomial that's just a sum over the rest of the variables, and is a univariate polynomial in just the variable in the first message, x1. And then the verifier essentially computes the rest of the sum. So if you look at this part, and yeah, if you would have some time to look at it, you will notice that this exactly finishes the computation of the entire sum. So then the verifier can check, OK, if this g1 evaluated at 0 plus g1 evaluated at 1 equals to h, OK, the prover was honest, all is good, let's continue on with the protocol. And then the verifier sends a random challenge. The prover replaces the first variable with this random challenge, and then they repeat the process with a polynomial that has one less variable. And like so until we run out of variables, and at the end we have some final check that checks, OK, is the polynomial evaluated at these random points actually equal to the final claim that we'll have at the end of each round? So yes, a lot of the times you might see this g1 evaluated at R1 or G2 evaluated at R2 as being just H1, H2. So those are just claims for the updated polynomial. And yeah, this is now much more efficient, but people want to make things even more efficient every time. And here comes the compression trick, which will later we will see that it can cause many problems because of that. So here in red, I have the constant term of the polynomial being sent over. So it is not multiplied by any power of x. And normally, it's, well, still part of the, where's the laser? Part of the proof. And then, yeah, the verifier will check, evaluate this g at 0, g at 1, and check if it is equal to the claim, and then set the next claim, here I denoted is at h prime, as g evaluated at some random challenge. But yeah, what happens? Can this work even if we do not send this A0? So yeah, in the compressed sum check here, you can see, well, that there isn't an A0 there, that we just send some G prime, a modified polynomial. But the verifier still wants to check if the statement holds for the original polynomial. So what we can do, well, just write out the equations. So we see that, yeah, if we remove just this A0, and if we sum up G evaluated at 0 and G evaluated at 1, if we add back this A0 twice, we should get back to H. And well, this just gives us an equation that if we turn it around a bit, we get this thing, which essentially tells the verifier that how to compute A0. And then, well, now that the verifier computed A0, they have all the data that the standard verifier had, so they can set H prime to be, well, set normally. But the caveat here is that on the left side, here the verifier checked that this relation actually holds. On the right side, the verifier assumed this equation holds and computes the value based on that assumption. So we remove a check, and instead just the verifier computes with the assumption that the check holds, and this then propagates all over. And then when we come to the last check, the last step of the sum check, that final statement will actually be checked. Before that, it will just get computed, and the verifier does not care if the prover cheated in the meantime, because when it gets to the final check, it should catch that with the final check. Now, the problem comes when, well, the random values used in the sum checks and in the evaluation of that polynomial actually do not depend on the input claim. So written a bit more concisely, the final claim of the protocol, so this Hn, is just a polynomial in the random challenges derived by the verifier and the input claim H. And it is linear in H. That is, we get an equation of this form where A and B are just something. And yeah, as I said, if the randomness here does not depend on H, well, or in other words, it's independent, this polynomial, the A and the B do not change if we change H. And the Hn also, what it should be for the verifier to check in the final stage of the sum check, because this is the final claim, it checks it against something, not really important what it is. And what is important is this part doesn't change, A doesn't change, B doesn't change if we change H. So since we know all of those three values, we can just pick whatever H satisfies this equation, and we have a valid proof that the verifier will accept. Now, in just this case, if we have just a single sum check running, this is not inherently that much of a problem, but well, zkVMs are complicated protocols. They have multiple sum checks, and then instead of one equation, one variable, which is usually a simple case, we'll have many equations with many variables, and we might be able to pick some H values in such a way that an honest prover for an actual execution of a problem would not be able to do. And then we can get into the funny parts of forging proofs. So yeah, this is basically next the kind of thought flow of how you exploit such bugs. Don't need to read all of it. Essentially, first you just need to find, OK, are there any variables that are not constraining the randomness? Or in other words, are there any variables that are not added to the Fiat-Shamir transcript? Because the Fiat-Shamir transcript determines the randomness, all of the random values in the protocol. So if there are any such values that are not appended to the transcript, well, we can then run the proof on some wrong values, some malicious values, see how it goes, and then change these unconstrained values afterwards, and the rest of the proof will not change, but maybe the final equation check will pass now, and we get a forgery. So this is exactly like in step 2. This usually turns out to be that we are looking for some polynomial equations to solve, some systems to solve. And then, yeah, in the rest, we just construct those systems based on what the proof looks like and get a forgery. So yeah, now let's go into the maybe more practical part of, well, what are these actual systems that my colleagues mostly managed to break, and some of these that I couldn't talk about because they're still in active disclosure and not patched yet. So firstly, we'll divide them into 2 kinds of systems. So sometimes you have a proof where some of the values in the proof are not bounded, so are not added to the Fiat-Shamir transcript. There you just change something in the proof and forge stuff that way. And the other one is even funnier, where some of the values that are crucial for the proofs are actually not part of the proof. They're added as auxiliary arguments to the verifier function. Those might be something like public inputs. OK, what was the program input? You might have a proof that does not depend on the program input at all. So if you just tell the verifier, oh, yeah, no, my input was actually something completely other than what I proved for, it might just accept it if that is the case, depending, of course, on what those inputs actually are. So let's take just a brief look at all of these systems that I have listed here. So why I spent so much time talking about sum checks and that compression trick that leads to mistakes is, for example, Jolt and some others after it as well, is a zkVM which heavily relies on use of compressed sum check. And of course, since I am talking about it, they forgot to put the claims of that sum check into the Fiat-Shamir transcript. So if you draw out how this entire proof system works, you just will end up with a system of equations which essentially just boils down to some polynomials equations, well, some equations in H for some fixed alphas all need to be 0. And yeah, OK, the notation might not be the nicest, but these kinds of systems you've been solving since middle school. Maybe with less variables and less equations than what we have here, but this is very basic mathematics. And it completely breaks the system. With such things, by solving this system, we managed to prove stuff like that 1 plus 1 equals 1,000. And, well, whatever other thing based on the program we wanted to prove stuff on, prove for any input arbitrary outputs. And the funny thing is, the patch to make this, well, to go from this being critically vulnerable and completely exploitable to it being completely secure is 1 line of code. Just add the input claims into the transcript. Just have these HIs hashed into the Fiat-Shamir transcript, and then we're all good. So yeah, essentially this is a diagram of part of how Jolt works. And here we can see opening claims. And well, the dotted line tells us there should be a line there, but it's not. And because it's not, and these claims are then only used down here when the verifier actually checks something, like the green boxes are going to be the actual final verifier checks, we can basically run the entirety of this proof on whatever data we want, whatever the prover makes up, and then change our minds on what this red box is for this last computation to succeed, for the verifier to be happy. So let's go on to the next one. The next zkVM we broke is Nexus, which works in a completely different way by splitting proving parts into many smaller parts, but that's not really that important. And then each component is verified independently using something called a logop argument, if anyone is interested, which looks basically like this. You will have some sum over 1 divided by something, but for the purpose of this presentation, that's not really needed, just an interesting thing if anyone is interested. And then the entire check is these 2 equations here. So as you can see, again, we just have some sum of something is equal to something else. So again, just a system of linear equations. And these claimed sum variables were not added to the transcript. So we can just, once we know all the alpha values, solve this system and prove whatever we want. And again, the patch was just a simple append this to the transcript, add a few more hashes to the code, and that's it. And again, yeah, here we can compute the entire proof because this dotted line here doesn't exist because, well, the claimed sums are not added to the transcript and are only used in the actual final computations after we've done all of the important parts of the verification. So I'll speed up a bit because now otherwise it will get very repetitive. CheiroM is another similar system based on the logop argument. Here we have an even uglier expression in the denominator. And well, the equations are not linear anymore because the variable that we can change is in the denominator, but still it's just some equations. Might be a bit harder to solve this time around, but still solvable and leads to us proving whatever statements we want. Again, the same we can see here like with the different parts of the protocol. We can just compute everything we want and then change our mind of what the red part is when the verifier checks stuff in the green part. Then in Seno, it's again just a small difference. We will have a system of equations. Only here we will have some products, which, yeah, now that we have a product of many variables, it might get more annoying. But if we just arbitrarily choose all variables except 2, we end up with these 2 equations. And as long as we know how to solve these 2, where everything but the x values is fixed and the x values are the solutions, I think everyone can manage to do this on pen and paper, and this will just let you forge anything. So it really can be that simple, unlike what the notation above would make you think. And then another proof system is Expander, which again just is based on a bunch of sum checks, and verification is then linear. So again, just system of equations. And Binius is very similar in that case in, well, just being linear in everything and using a bunch of sum check protocols. So now let's take a look at what actually happened once we found these vulnerabilities. So yeah, all of those were reported to the maintainers. All of these are open source projects, some of them in production, some of them still in alpha stages. And as you can see in response times, most of these maintainers actually do care about their project and fix their bugs quickly. We don't talk about Seno though. And yeah, I think less than a week to fix a critical vulnerability sounds like a reasonable thing to do. But yeah, this list will keep growing. We've been doing more research afterwards, but yeah, it didn't end up on these slides. You might find more in the future if you follow what we're doing. But yeah, why does this happen? Like this, while the equations of how this all works might be scary looking, the math behind this is actually trivial. It's just a system of equations, sometimes even just 2 equations, 2 variables, which we've all seen before. Well, the thing is, the first rule of, well, zero knowledge proofs is try to make everything fast. But optimization can, well, lead to bad things. Remove something, like if you don't add something to the transcript, that's gonna give you some performance, but it might completely break your proof. And that usually comes with, well, not being careful enough when going from an interactive protocol, which is usually just in theory written as a two-party protocol, and going into the non-interactive part, so adding the Fiat-Shamir transform, where that's then usually not written in the papers that define these protocols, and the implementations have to figure out their own way of how to do it. And another thing is that while these things might not be hard to exploit, detecting these bugs by stuff like fuzzing or running tests is basically impossible because, well, we still need to solve that system of equations, which is not going to solve itself with randomly mutating the inputs. And yeah, so the key takeaways of this talk for the finish is that, yeah, Fiat-Shamir bugs are extremely common. Everyone messes it up. If you've played any crypto CTF challenges that involve zero knowledge, you will know that it's always Fiat-Shamir's fault. And a lot of the times, the fixes to these bugs are actually trivial. Just add one line of code, append something to the transcript, and we're secure. So please, if you're designing anything that's using Fiat-Shamir, just hash everything. Append everything to the transcript. You might lose some percentage of performance, but it's better to be safe than to be completely exploited. So yeah, that's all from my side. And if there's any questions, I would love to take them.
Do we have any questions? Yeah. I think you might get a prize for the most questions asked.
Yeah, possibly. So I'm not sure if this is like the same field or the same subject, but like the only practical application of zkVMs that I heard is that I think Signal's founder created some sort of a chatbot that runs, that is supposed to run an LLM in a zero knowledge proof virtual machine, so that you could prove that your chats with this LLM that wasn't running locally but on another server, they could still prove that this chat stayed private. But I'm not sure if that's the same thing or not.
I'm not aware of that project, but yeah, the way you described, yeah, it's essentially what is doing. Yeah, it's you want to prove that if you ask a chatbot something, it will answer with what it actually answered, and that it was that chatbot that answered that, and not some other one. It is essentially what this is meant to do. Yes.
Yeah, it's called I think it's Confer or something like that.
Yeah, okay. Not familiar with that. Sorry.
Any more questions? If not, thank you, Andraž.